Hello, everyone. Welcome to another day of the SMaRT seminar series. It's my pleasure to welcome Dr. Alex Albert. He is a postdoctoral researcher in the Predictive Science Lab at the School of Mechanical Engineering at Purdue University. He also earned his PhD from Purdue University in 2024 under the supervision of Dr. Elias Bilionis. Before joining Purdue in 2019, he has earned his bachelor's and master's in applied mathematics at the University of Akron while being advised by Dr. J. Patrick Wilbur. His research focuses on techniques for inverse problems and scientific machine learning, primarily through information field theory. Now, with that brief introduction, please join me in welcoming Alex for this presentation. And the field is all yours, Alex. Thank you so much.
Okay. First off, thank you for the invitation to the seminar. I'm very excited to talk about this work today, which has recently been published, so it's kind of brand new, the most recent thing that I have been working on. So the topic of this talk is how we can build meaningful or interpretable priors for Bayesian neural networks. And we do this through the lens of information field theory, which is a new theory for Bayesian inverse problems or Bayesian inference that we have spent the better part of maybe 5 years developing. And it's nice to see sort of the first culmination and results of this work. So first, I want to try to motivate why we care about assigning interpretable priors to Bayesian neural networks, or why we care about uncertainty quantification for neural networks in general. So in scientific and engineering settings, it's very often the case that simple point predictions from your neural network are not enough. So this is because many tasks or systems that we like to predict on have limited and noisy data. And they could be sensitive. So the cost of making the wrong decision could be much higher than the cost of saying, I don't know the answer to this problem. So along with this, you often need to answer how certain is your prediction, and you like to understand where is your model extrapolating, and then also maybe how does your uncertainty propagate into downstream decisions or downstream quantities of interest. So yeah, deterministic neural networks can interpolate very well, but in a lot of these applications, the object of interest is not only the mean prediction, but we want some confidence along with that prediction and a principled way to encode uncertainty quantification. So these are important in applications involving things such as surrogate modeling. Ill-posed inverse problems is something that I work on a lot, or a PDE constrained inference. So an example from our group, which comes from another postdoc in my group, Atharv, so they finished this work recently, is this methodology for reconstructing hemodynamics from 4D flow MRI videos, which they call SMaRT. And what SMaRT does is it takes extremely noisy images or videos coming from an MRI, and then you try to simultaneously reconstruct the velocity and pressure field of the blood flow through an aneurysm while also reconstructing the geometry. So this is a medical application where it would be quite important to have some degree of confidence in your solution. Right now, SMaRT only gives you a deterministic point estimate, but with the sort of method I'm talking about today, you can now bake uncertainty quantification into this hemodynamic flow reconstruction. So the kind of standard paradigm when you want to work with Bayesian with neural networks and UQ is to just work with a Bayesian neural network. And how these work is you essentially just treat the parameters of your neural network as a random variable. So then the output of the neural network is now a stochastic process that you treat as a probability distribution, and then you construct a posterior distribution by conditioning this prior over the data. But the complex input to output map of a neural network makes it very difficult to choose the right prior, because you don't care about what the prior on your network parameters looks like. When you start making predictions, you care about what this enforces in the output space of the neural network, in the actual function space that your neural network samples live in. But because you start with a prior on the network parameters, and then this prior goes through many different nonlinear transformations as it passes through the neural network, it's hard to understand sort of the constraints this is enforcing. And of course, when you are doing any Bayesian methodology, having the right prior distribution is key. So oftentimes, we just simply default to independent and identically distributed Gaussian over all of the parameters, and we call that our Bayesian neural network. Now, Gaussian processes, on the other hand, is kind of an alternative competitor to Bayesian neural networks, which many people prefer due to their interpretability, meaning that all of the behavior of the Gaussian process in your function space is completely determined by the covariance kernel. You say, before I observe any data, I think the field I'm trying to reconstruct has certain properties, whether it's smoothness, length scale, periodicity, that sort of thing. And then you can select the right covariance kernel so that your GP obeys these properties. And of course, they also have nice analytical posteriors under certain assumptions where, in a lot of cases, your posterior you obtain is also a Gaussian process. Now, unfortunately, as much as we like Gaussian processes, they oftentimes cannot scale to large data sets very easily. This is because if you want to train or sample your GP, then you have to start inverting very large covariance matrices. And methods which allow you to do this, they often require the covariance matrix to have a specific structure, so it can be quite limited. So now I'm going to talk about the examples that I kind of have in mind, which is just a simple regression task where you have some deterministic target function, and then you have noisy observations of that function. And here I'm using this measurement operator R to remind you of the fact that many times the measurements may be nonlinear, which makes the inverse problem a lot more difficult. So then we define a Bayesian neural network as a stochastic process where I have some activation function H, and then you build a neural network architecture however you like. And then I treat all of the parameters as a neural network of the neural network, which I have consolidated into this vector theta, as a random variable with a prior distribution, and then you apply Bayes' rule to get a posterior over the network parameters. Now, there's a very deep connection between Bayesian neural networks and Gaussian processes, where it is known that wide neural network or Bayesian neural networks become Gaussian processes, meaning that if you follow the standard paradigm where you pick a IID Gaussian over the network weights. So this is because it's difficult to assess the inductive bias, which is enforced by your prior over the network parameters. So we often default to this choice. And then what happens is that if you send the number of neurons in a layer to infinity, then your Bayesian neural network converges in distribution to a specific Gaussian process, which is centered, and it has a covariance kernel with this form. So here, the covariance kernel is governed basically entirely by the activation function that you have picked to construct your Bayesian neural network. And then this is known as the neural network GP, or NNGP. Now, I'll go through an example of NNGP where we know what the covariance that you get through this limiting procedure is explicitly, to show you that it's not as useful as you would think. So these are kind of meaningless for the common activation functions that we like to use in machine learning. So if we start with ReLU, then this is one of the very few examples where the NNGP is explicitly known. So we know that if you take a ReLU network and you send the number of neurons in a layer to infinity, then this converges to a GP with the arc cosine 1 kernel. So then these are what samples from that Gaussian process looks like, and you can kind of see what kind of inductive bias this is enforcing. Now, let's study the covariance kernel of this Gaussian process in detail because, again, the covariance kernel of the Gaussian process completely determines how it performs in regression and all of the properties of that. So the arc cosine 1 kernel is actually a very bad kernel for regression. So it looks like this form. We have these norms and we have these sines and cosines. Now, if you fix one of the inputs, so here I fix t to be 0, and then I plot how the kernel looks as a function of the other variable, then you can notice that as you move your points apart, the covariance actually grows. So this is kind of the exact opposite behavior that we would want when we're doing any kind of regression task, where if we have points that are closer together, we would want them to be more correlated. And as the points grow further apart, we want that correlation to completely die off. But this kernel gives you the opposite behavior. So it's not a very good choice. So what this means is that if you have a specific Gaussian process in mind, and you want your Bayesian neural network to limit to that Gaussian process, and you treat the parameters as an IID Gaussian in the usual manner, then you have to cook up the right activation function so that it limits to the correct GP. This is expensive and difficult, and it's kind of on a case-by-case basis. So an example of this work for an incoming faculty at Purdue is Sasha Renfeld has written a paper on this work where you can make activation functions so that your Bayesian neural network are physically consistent and that sort of thing. So then I look for an alternative view, which is to say, I don't want to have to start cooking up difficult activation functions. What if I instead design the parameter distribution so that the BNN with any architecture that I want approximates a GP? And that's what this work is about. So we approach this through the lens of information field theory, which I will give you a quick primer on what we're doing here. So IFT takes inspiration from physics, where we work with path integrals, which are basically formally defined measures in infinite dimensions. So the physicist viewpoint of a path integral is just an infinite limit of finite dimensional integrals. These, of course, were made famous by Feynman in his thesis and the path integral construction of quantum field theory. And then this idea was kind of first proposed very early on in the 1900s by Daniel. So the high-level idea is let's treat Bayesian inverse problems as field theories to say, I want to start with an infinite dimensional probability measure, which, say, for example, is a Gaussian process. And then I want to work with it as if it's a finite dimensional distribution, so I can use things like Bayes' rule, write down probability densities of these objects. And so if you believe in path integrals, then you are permitted to do this. This idea was first proposed in the book on Bayesian field theory by Lem. And then later, Torsten Enschlen of the Max Planck Institute for Astrophysics over in Munich then really expanded this idea where his applications are nonlinear signal analysis for astrophysics, where they're trying to do things like reconstruct the gamma radiation of the galaxy and this sort of thing. So classical information field theory, which is what this work is based on, I kind of view it as a physicist Gaussian process regression. So IFT is just Bayesian statistics over fields using the path integral formalism. And in the classic case, we just stick to Gaussian processes. So we want to define probability measures over the space of field configurations using these path integrals. So we do this by writing down a formal Lebesgue density where I say my probability distribution over functions has a form that looks like this Gibbs measure, where E is in the IFT literature, it's referred to as an information Hamiltonian because, I mean, the work is rooted in physics, so physicists were the one using this first. But we might know it as the potential function or the Onsager-Maclap functional. And then the normalization constant of this measure is called the partition function and is given through a path integral. Now, you can use this to represent Gaussian measures. So you think about what would the probability distribution or the density of a Gaussian process look like. So you just start with the finite dimensional multivariate Gaussian case, which is defined as, right, I mean, you have this inner product between the vector, and then you have the inverse of the covariance matrix, and then the vector again. So you do this, but now you extend your inner product to the L2 inner product because your vector becomes a function, and then your covariance matrix now becomes a covariance operator. So you write down this form, and it turns out that through various limiting procedures, this is a rare case of path integration where you can actually make this object well-defined as an abstract Wiener measure. You can go read the classical book by Gluman Jaffe to understand how this works. Now, how we represent finite dimensional approximations to these measures in classical IFT is essentially through projections onto meshes of L2. So what we have been doing in the past is we have this IFT prior, which lives in infinite dimensions. If we want to start doing inference on a computer, you have to approximate that somehow. So you basically pick an orthonormal basis of L2, and then we consider the finite dimensional subspaces, which are defined by the span of that basis up to some truncation. And then you say, I'm going to project my measure onto that space. So now I have a finite dimensional space, and my measure is now well-defined because you can just rely on the Lebesgue measure in finite dimensions. So we were able to prove that under this parameterization, you actually converge to the correct Gaussian measure in the limit of infinite basis functions. So to do this, of course, you have projected your measure, so now your covariance operator becomes a covariance matrix when projected onto this space. And so now we have a finite dimensional Gaussian distribution, which is approximating the Gaussian process that we start with. It has the same type of form. And then we can show that the finite dimensional representation has the correct limiting behavior, in that if I take my Gaussian process that I start with and I restrict it onto a small space, say with dimension 3, and then I take that measure and I restrict it to a small space with dimension 5, then it hasn't changed how that measure behaves on the first 3 basis functions. So you're just adding more behaviors, you add more basis functions, and it doesn't change how it depends on the original space. So then the parameterization completely determines where these subspaces are defined. And then if you redefine the mesh by adding more basis functions, it doesn't change the behavior of the prior when restricted to the original subspace. So this basically means that in applications, there is some cutoff point where adding more parameters to your approximation doesn't really benefit you. You have diminishing returns. And in the language of physics, we call this an ultraviolet cutoff. And now we prove that the finite dimensional IFT prior converges to the correct Gaussian measure. So you can show that if you take your Gaussian process and you approximate it using our basis term, then the measures essentially converge to the correct Gaussian measure on L2. So you use this by proving with the characteristic functions. So each of these projected measures is essentially a finite dimensional Gaussian distribution. So we can write down a characteristic function, which looks like this. It's easy to see in the limit that this thing converges to the correct characteristic function of the Gaussian measure that we are after. And then because we have convergence in characteristic function, we have convergence in measure. And then we can also prove that the posterior converges in the correct way, meaning that if I write down the posterior that I get from Gaussian process regression, and then I start, instead of with a Gaussian process, I start with my finite dimensional approximation coming from this spectral expansion. And then I write down that posterior, then the finite dimensional posterior converges to the posterior as if I started with Gaussian process regression. And we show this in terms of the Wasserstein distance. And our result relies on this following lemma from this paper, which essentially says that if you have a finite dimensional approximation of your prior and you converge, and you prove that your finite dimensional prior converges in Wasserstein distance to the prior in infinite dimensions, then you also have convergence in the posterior. So we know that our sequence of priors that we get from our finite dimensional approximation converges in the Wasserstein metric if they converge in measure, which is what we've shown. And you also need to show little things like the moments converge, and this is very easy to prove with the Fernig theorem. So putting everything together, we show that our finite dimensional approximation converges to the correct object, so we are justified in representing our Gaussian processes in this way. So now in this work, we extend this idea and we replace our basis with a neural network so that it's more expressive. So that's where we come up with this new prior for Bayesian neural networks, which we term the Mercer prior, and we'll see why later. So we take the IFT representation of a Gaussian process, and now I replace the field with a Bayesian neural network. So now I have a distribution over my neural network parameters, which has the form of basically a full rank Gaussian distribution, where now S is the covariance operator, which is induced by the kernel. So I start with the Gaussian process, and then I find this associated covariance operator S, which just has the kernel K. And then the prior is defined by the inverse of this operator. Now, what makes this work difficult is that the inverse covariance is not trivial to evaluate, because if you start with a generic covariance kernel, then you'd have to go and find the inverse of that, and that's a very difficult problem. So instead, we built a specialized sampler using stochastic gradient Langevin dynamics, which has a nice characteristic or characterization of the inverse covariance. So we're going to use SGLD to sample this distribution. So SGLD just requires you to have an unbiased estimate of the gradient of the log of your distribution, which in our case, we just have this quadratic form. So I'm going to build an unbiased estimate of this quadratic form up at the top. So the integrals are pretty easy and can be approximated with the usual importance sampling, right? Because on the outside, I have an L2 inner product, which is just an integral. And then I also have to apply the inverse covariance to the Bayesian neural network, which again is governed by an integral. So you can just get those using importance sampling. Now, I also need to represent the inverse covariance kernel. And this is a lot more involved. And for this, we rely on Mercer's theorem to represent it. So because S is a valid covariance operator of a Gaussian measure, then we know that the spectral theorem holds and that I can write down S using its eigenvalues and eigenfunctions. And so this also means that Mercer's theorem holds, and I can take my covariance kernel and I can express it as this infinite series up top, which is just defined by the eigenvalues and the eigenfunctions of the covariance operator. So if I know those, then I can replace the inverse covariance with this. So then the inverse covariance can just be written in this way, where you just turn the eigenvalues and eigenfunctions upside down, or sorry, you turn the eigenvalues upside down and they have the same eigenfunctions. So I will be using this to represent the operator of the inverse covariance. So now we come up with this unbiased estimate, which has a very, very long form to look at. But essentially what's going on here is I'm using importance sampling for the integrals, meaning the L2 inner products that appear. So that's what these terms, the sums over M are. And then on the outside, I need to sum over the eigenvalues and eigenfunctions of the covariance kernel. And I build an estimate by treating everything as an expectation. So I turn my L2 inner products into expectations using importance sampling. And then I have this infinite series, which is defining the covariance kernel. So then I write this as an expectation over a discrete random variable, which is supported on the entirety of the natural numbers, and then I just build a sampling average approximation of that. So now in the end, we just have this nested summation, and everything can be computed quite easily. So we'll go through the algorithm in great detail to see how this works. So we're using SGLD. So first you initialize your Bayesian neural network parameters to some initial point, and then you also have to set your SGLD learning rate. So then to step through a single sample of this prior, first you have to sample your L2 inner product mini batches, which again are giving those integrals. So I just sample them from some uniform distribution over the domain. And then you also need to sample a spectral index mini batch so that we can build an unbiased estimate of the inverse covariance. So I'm just sampling basically indices which will give me random eigenvalues and eigenfunctions of the inverse covariance. And you sample those from a discrete distribution. So now, once I've identified my random eigenvalues and eigenfunctions, I compute inner product estimators. So I'm using these sums where I take my Bayesian neural network, I multiply it by a random eigenfunction, and then I basically am doing the L2 inner product between my Bayesian neural network and a randomly chosen eigenfunction. And then you do this many times. And then you put everything together to form an unbiased Monte Carlo estimator of the entire thing. And then with SGLD, all you have to do is take the gradients of this guy and then update it like it's stochastic gradient descent, but then you have some injected noise so that SGLD converges to the correct distribution. And that's how we actually sample this in practice. So now let's look at the computational cost of doing this. So in general, to generate an independent sample from a posterior predictive distribution that you would like, it has this leading order cost where we're basically linear in everything, where you have to consider basically the number of Bayesian neural network parameters that you pick. And then you also need to consider the domain mini batch size and the eigenpair mini batch size and the data mini batch size. And because you are using SGLD, in principle, this will converge for all of these mini batch sizes chosen to be 1. Now, this means you would need many more SGLD steps, but you could use a mini batch size of 1. And then I also multiplied by the number of SGLD steps per independent sample because SGLD is known to mix very poorly, and you could implement something like preconditioning to improve that performance. And then in the end, the important part is it's linear in the number of test points. So after you generate an independent sample, you can say, I want to take my sample, which is a Bayesian neural network, which again is a very good approximation of a target Gaussian process. It's now linear in the number of test points that you want to evaluate that on, whereas a Gaussian process in the naive way is actually cubic in this. So you reduced the computational cost of evaluating the posterior predictive distribution by a ton. And then in the paper, we kind of compare how this method compares to basically naive Gaussian process regression, and then also KISS-GP, which is one of the most scalable algorithms out there. So I designed 2 scenarios where I'm picking kind of the 2 extreme ends of these hyperparameter choices up here. And then we say, okay, when would we surpass the power of an NVIDIA H100 GPU? And we find that as a function of number of test points, our method can reach basically billions with ease before it surpasses what this GPU could handle. Now, we'll talk about kernel choices because the catch with this method is that it does require you to know the eigenvalues and the eigenfunctions of the kernel. So you have a target Gaussian process that you are after, and you want to approximate it with a Bayesian neural network. Well, with this method, you can do that if you can access the eigenvalues and eigenfunctions of that kernel. And then, unfortunately, for a lot of common choices, these are not quite easily available. But you could do so using something like the Nystrom approximation if you are willing to put in the effort and pay the cost upfront to find them. Most of the time, we are just sticking to kernels which are based on the negative Laplacian, which is kind of the gold standard that's used in the Bayesian formulation of physics-based inverse problems, right? So our baseline Gaussian prior is a Gaussian measure over L2 with a covariance kernel given by the inverse Laplacian raised to some power alpha. So this has eigenvalues and eigenfunctions, which look like this. So the eigenfunctions are just sines and cosines, which are quite easy to compute. And then you take these eigenvalues and you just raise them to the power alpha. And then if you want to see what this prior is enforcing in the output space, you can rely on Sobolev embedding theorems. So basically, alpha is determining how differentiable your samples from this prior are. So now I have everything set up. We do a deep dive where we draw Bayesian neural networks from Brownian motion, which I think at least is a very cool baseline to observe. So we want to take our Bayesian neural networks and draw them from Brownian motion. So we need the eigenvalues and eigenfunctions. These are well known. They just look like this. So now I can plug these into the Mercer prior and start sampling my Bayesian neural networks. Now, in practice, I don't actually consider using infinite eigenpairs. I truncate the Mercer representation of Brownian motion kernel at some point. Otherwise, you would have a small chance of sampling an eigenvalue that would be beyond computer precision, that then something would break. So I truncate it at some point. And then I start sampling my Bayesian neural networks from this Mercer prior and study how well it does at approximating draws from Brownian motion. And then I do this depending on both the width and the number of eigenpairs that I keep because I am truncating that expansion. And then you can see the paper for all of the details. So this is kind of the highest fidelity approximation that we get, where on the left I have exact draws from Brownian motion using Euler-Murayama on 10,000 points. And then on the right, I have my Bayesian neural networks, which are drawn from my corresponding Mercer prior. And here I keep 1,000 terms in the expansion, so the Mercer expansion of the kernel of Brownian motion. And then I'm using a single layer network with 2,500 neurons. So empirically, we find that shallow neural networks tend to outperform long neural networks in this work. And then to show that it scales well, I evaluate each of these Bayesian neural network samples on 100,000 points, which is a bit ridiculous. But now we develop some statistical tests to understand how well this is actually approximating, because, I mean, from the picture that we get, it looks kind of passes the eyeball test, but let's dive into the statistics. So because we're trying to approximate a Gaussian process, I think the most important test is to see that the empirical covariance matrix of my Bayesian neural network samples matches the true covariance. And this is because Brownian motion is a Gaussian process, and Gaussian processes are completely determined by the behavior of the covariance kernel. So if these two things line up, then nobody can convince me that I'm not approximating the correct Gaussian process. So on the leftmost figure, I have the true covariance of Brownian motion, and then in the middle, I have my empirical covariance I get from my Bayesian neural network samples. And you can see that it does very well, and we have very little error. The only thing that is off is that the empirical covariance is a little bit more wiggly than the true covariance, but it might be hard to see in this figure. And you can also observe this by the fact that the majority of the error in the covariance is along the center line. And this is just saying that we are unable to capture the extremely high frequencies. So we get most of the frequencies, but we can't get all of the frequencies. And then we also check that the distribution matches on certain time slices, because we know at any time t, the possible values of a Brownian motion should follow this Gaussian distribution. And then so on the left, I compare the histogram that I get from my Bayesian neural network samples with the ground truth distribution at those times. And then I also use a two-way Kolmogorov-Smirnov statistic test to determine basically, are we within range of approximating Brownian motion? And we see that, yes, we do. So now we study how this prior depends on the number of eigenpairs that you keep. So basically, if you use too few terms, then the Bayesian neural network cannot capture the higher frequencies because you've truncated those off. So for example, if I keep only 20 terms, then these are what my samples look like. You can observe here that these are kind of following the overall trend of how we expect Brownian motion to behave in the long term, but we don't get any of the high frequencies because you basically thrown them away. And then now I use an identical architecture for my neural networks, and then I change the number of eigenpairs and see what happens. So this is how these behave. So we can observe that even after only picking 100 eigenpairs, we have a pretty good approximation of what Brownian motion is supposed to do from the empirical covariance. Now, we also then study how it depends on the network width. So I fix the number of eigenpairs to the default 1000 that we found worked best. And now I'm using a single layer network with a different amount of neurons in that first layer. So I go 100, 500, 1000, 2500. And then what we expect is that we should observe convergence as the number of neurons goes to infinity. And you can see that here qualitatively, that as we add more neurons in the layer, then our approximation starts to look more and more like Brownian motion. And we get that from the empirical covariance plots where the error starts to decrease and we get less than 5% error once the network is wide enough. So we're seeing some kind of limit theorem here. Okay, so now that we've studied that, let's go over a few example applications that I'd like to talk about. So I'll pick applications where it would be beneficial to replace a Gaussian process with a Bayesian neural network. So these applications feature something like hierarchical Gaussian process regression with heteroscedastic noise. So I have basically Gaussian processes which are nested within each other. So this would be very difficult to characterize if you're using, if you're sticking to GPs. And then I'm also going to look at time series prediction on data with a periodic structure to show that our Bayesian neural network with the Mercer prior outperforms the vanilla Bayesian neural network. And then I'll also get into a nonlinear elliptic PDE inverse problem. So for the hierarchical Gaussian process regression example, I take a data set that consists of acceleration measurements of a helmet during a motorcycle crash. And then this data is well known to have heteroscedastic noise. So I have a hierarchical Bayesian model where the likelihood of an individual observation is, we're not treating it as a Gaussian, but with a mean and a variance that depends on time. So then I represent both the mean and the standard deviation of this likelihood as centered Gaussian processes, where I'm using this negative Laplacian kernel. And this places the assumption that both of these live in the space H1. So I'm basically saying at the minimum, I would like the mean function and the standard deviation to have one derivative. And so then you can apply Bayes' rule and get the posterior. So after I represent these Gaussian process priors with my Bayesian neural network, then I can write down the posterior over the network parameters and start sampling from this. So this is the result. So on the left, I have samples from the prior mean function, so you can see how these sample paths look like. And then on the right, I have the posterior and compared to the data, and you can see that we're able to perform hierarchical Gaussian process regression quite well, and we capture the heteroscedastic noise in this data set. And then to show its scales, I then evaluate the posterior predictive distribution on 1 million points, which would be completely out of the question if you stuck to Gaussian processes. So now we compare our Bayesian neural networks to the standard paradigm. And we do this by looking at data that has a periodic structure. So this data set consists of atmospheric CO2 concentration levels at an observatory in Hawaii. And so I take 4 years of this data set as training data, and then I want to predict 2 years on into the future. So I need a Bayesian neural, or I need a prior which can capture periodic eigenvalues or periodic behavior. So I engineer a custom kernel from predetermined orthonormal functions, which look like this. So the n=1 term is associated with eigenvalues and eigenfunctions with the same period as the data, so that the bare minimum, our kernel is able to capture the period of the data, and then I decay the eigenvalues exponentially to discourage the Bayesian neural network from learning higher frequencies. So in this example, I'm trying to show you that even though you need to come up with eigenvalues and eigenfunctions, you can use basically first principles to then actually engineer these eigenvalues and eigenfunctions to perform certain tasks. So then I derive the posterior and I compare it to the standard method where in the middle, I have the posterior that I get from using the Mercer prior with these eigensystem. And then on the right, I compare it to how a basic Bayesian neural network behaves. And I can see that after we are done observing the data, we still are able to capture the periodic trends that we would expect, whereas the regular Bayesian neural network just goes and does whatever it wants because it cannot extrapolate. So now, final application is on a nonlinear Bayesian inverse problem, where I'm working together with collaborators from NASA, where we want to develop new installation for basically re-entry vehicles. So this is one type of installation. And to do this, we have somebody in the lab come up with a new installation, and then we need to understand the thermal properties of that installation from temperature measurements, so then we can understand how it would perform in practice. So then they do this by collecting temperature data in the lab, and then this gives us an inverse problem that involves the heat equation. So the problem set up is they go in the lab, they put this installation into some device, and then they heat up one side, cool the other side, and they measure the temperature at some points throughout. This is known to follow the nonlinear heat equation, where the thermal conductivity actually depends on the temperature. And so I represent the conductivity with a Gaussian measure on L2. So with this prior, I'm enforcing the fact that the thermal conductivity should be differentiable so that the heat equation is well defined, right? So then I take their data and I start, and then I solve this nonlinear Bayesian inverse problem with our method. So I take the Gaussian prior and I replace it with a Bayesian neural network with corresponding Mercer prior. So then the posterior over the network parameters is given in this way, where that P of theta is our Mercer prior. And now this problem is difficult under the usual Gaussian measure approach because R is a nonlinear PDE. So it's given by the solution of the nonlinear heat equation. So if you stuck two Gaussian processes, then you wouldn't be able to write down the posterior in a nice way, and you would actually be forced to sample. So if we're sampling, we might as well use our Bayesian neural networks because we can then use SGLD and scale it very well. So then we find that we're able to reconstruct the thermal conductivity from just the temperature measurements quite well. Now, there is some error once the temperature gets high enough, but that's to be expected because, I mean, this, at the end of the day, this is data that came from a real world experiment where somebody measured the temperature in the lab. So we would expect it to not be perfect. Okay, so to wrap things up, so we've essentially developed a new paradigm for Bayesian neural network priors, which approximate desired Gaussian processes. And the key idea here is to represent the Gaussian process with a formal Lebesgue density using the language of IFT. And then we replace this with a distribution over the Bayesian neural network parameters. And then application of Mercer's theorem gives us a nice representation for the inverse covariance term. And then I developed a scalable posterior sampling scheme using SGLD, which just takes sampling average approximations of everything. So remaining challenges with this method is that some popular kernels currently might be inaccessible. And this is because the method relies on the eigenvalues and eigenfunctions of that kernel being available to you. And the Nystrom approximation to find them may not always be practical because you may need a ton of eigenvalues and eigenfunctions. So an example is the squared exponential kernel, which is kind of the most commonly used one. So it actually has known eigenvalues and eigenfunctions if you work under a Gaussian measure. But when we tried this, we found that it was a bit too unstable to implement because you needed so many eigenfunctions that their normalization constants started to get way too big to work with. And then also, hyperparameter training is just something that I haven't talked about. It's quite difficult. And this is because the prior normalization constant now has a very difficult looking form where you have to integrate this kind of Gibbs measure looking form over the space of all neural network parameters. So this is kind of hopeless to do. And then if you wanted to learn the hyperparameters, you would write down your joint posterior and then maybe take maximum likelihood or evidence approximation of them. So that's what this joint looks like, where this normalization constant looks like. So if you want to characterize this joint, you would need access to this integral from the normalization constant, which is quite intractable to do. Now, it is possible to actually train this using a nested approach, which you can go read about in the paper. So that's everything that I have. Again, I'd like to thank you for your time. And these are the papers that this work was based off today. So one of them on the actual neural networks themselves is now published in CMAIM. And then the paper where I was speaking on the theory at the start was actually just accepted for publication yesterday. So, all right, thank you.
Thank you, Alex. This was wonderful. I'll open the floor for discussion. Maybe we can start with Shovik. I'm super sure he has a lot of questions.
But yeah, I have a few questions.
Yeah.
Yeah, I saw the paper. It got accepted, so congrats on that. So I think Elias posted the not ChatGPT. I think OpenClaw could not solve this this paper, right? The agents. I think this is what they want.
Yes, yes.
So yeah, congrats on that. So very interesting work. The idea of right using this Mercer prior to approximate any Gaussian process, right? That is the, I think, at the heart of this whole idea.
Yes, exactly.
But what I was wondering is maybe one more step. So suppose I have some prior knowledge, right? I mean, and in mechanics and physics, those prior knowledge often comes in form of differential equation. Maybe the parameters are unknown, but I have some knowledge about the physics of the problem in form of differential equation. So from there, can I go to the Mercer prior so that the Mercer prior now represents, because the parameters are not known. So if the parameters are uncertain, then the solution is like a stochastic process. It's a stochastic process. So can the Mercer prior do that? Because then it will be able to act as a prior for any, or at least most mechanics problem or
yes.
problem.
So the thing with this prior is that it's kind of set up uniquely to work with Gaussian processes because you need to rely on Mercer's theorem to represent the covariance kernel so that you can actually write down the prior and sample it. So if you could describe your state of knowledge about the physics as a Gaussian process, then you could essentially do this. Now, if you wanted to use a prior that encodes different physical knowledge that cannot be described as a Gaussian process, then you could go and you could use essentially like principles from IFT to write down what's known as a physics-informed prior, and you can go check out our other papers where we do this. But again, those are still kind of difficult to characterize. So I like this idea for Gaussian processes because one, we know that the infinite dimensional objects are actually well defined, unlike if you worked with a prior directly from the physics. And two, it gives us a way to actually work with Gaussian processes in a scalable way, which is kind of still an open challenge.
Yeah. So I think for some PDs, you can actually write a kernel. You can find the equivalent kernel. At least for some linear PDs, it is possible. So for that, obviously, this is directly applicable.
Exactly. Yeah. As long as the PD has a Green's function, you can find
Yeah.
you can find a Gaussian process that would go along with it.
Yeah. So then I was noting down some questions. So you said that you are using importance sampling, right? To approximate one of the Monte Carlo integration.
Yes.
So one of the challenges that we face in importance sampling is to find out what is the optimal importance sampling density. So can you shed some light on that what you are doing there? Because you have to assume like you sample from some distribution or with some,
Yeah, I
and
mean,
then you
to be honest, when I did this work, I just stuck to uniform distribution. I mean, I didn't bother to check because I mean, I know even if you pick uniform distribution, it will still converge to the correct thing. So
yeah, it will always converge. The only thing is that in how many samples. So maybe so
yes.
basically there is some scope for improvement probably. I mean, maybe with a better ISD, you will probably need even less samples, so even more efficient. Because
Yeah,
it's a function of number of samples, right?
Yeah,
Okay.
yeah, it's a function of number of samples.
Then scalability was excellent. I think up to billion or something you showed, right? With 800 or 800, I think.
Yes.
GP. So those are scalars, right? When you say 1 million or up to a billion, right? So that is scalars, because let's say each sample can also be a time series. So in that case, so this number was for scalars, right?
This number was number of test points in your domain that you want to evaluate a sample from the posterior on.
Okay. But each test point can be a field also, right? So even in that case, it holds, correct?
Well, then you're kind of dealing with operators, right? I mean, you would be sampling operators, which then you evaluate on fields.
Yeah, something like that.
Which may be something different. You'd have, I mean, you would probably need to generalize the prior to like operator learning to then understand this.
Yeah, but operator, maybe even a vector, right? It can be a vector also.
Yeah, I mean, if it's a vector, then you're dealing with essentially a domain in 3D or 4D. And the scalability of a neural network doesn't depend on the size of its input for the most part. I mean, if you give it 1 point or 3 points, that doesn't matter. I mean, at most, you probably have 4 because we live in 4D. So you would still have scalability to the billions.
Okay. So this hierarchical GP, right? So the concept is very similar to deep GP, the hierarchical GP that you are presenting, because deep GP also you stack GPs, right, on one over the other.
But yes, I mean this one is a little bit simpler where I'm not nesting Gaussian processes inside of each other. I'm taking the standard or a one-dimensional Gaussian distribution, and I'm writing the mean and the variance as functions of time.
Oh, okay.
But I mean, it's easy to see how this idea would extend to deep Gaussian processes as well.
No, yeah. Lastly, in the practical example, right? I think yes, the result is not matching at the end, and that is expected because it's real world data. So different types of noise and all of those things, and measurement error can also come in. But yeah, this one. But I was wondering that, I mean, in the ideal world, I will also like that it need not match, but it should be inside the confidence interval, right? So any reason why is it not? I mean, there is probably some uncertainty that we are not capturing here.
I mean, so the short answer is that we have a nonlinear Bayesian inverse problem where I want to identify a field that is unobserved, and I have 5 temperature measurements to do this. So, I mean, this problem is extremely difficult.
Yeah, it's a very challenging.
So, I mean, you could argue, okay, I can pick a different prior. So if you picked a prior with higher variance, then you would have higher uncertainty in the output of the posterior. But then I think you're getting into the weeds too much and you are maybe enforcing too much inductive bias.
Yeah. Okay. No, I was actually trying to understand if there is some uncertainty that is getting missed out. But yeah, I got it. I
mean, it could result from the actual experiment themselves because.
Yeah. I think that is all. Yeah, those are all my questions, but others might have questions.
I already see Savan putting his question on the chat box. So, Savan, if you're online, why don't you ask your question?
Its connection to Hilbert space that also exploit the Laplacian eigenbasis.
I see him online.
He's online, but maybe his mic is not working, so that's fine. I think you can read it.
Yeah. So, Savan, who is Shovik's student, he has a question for you, Alex. He is curious to know about the connection of this work to Hilbert space Gaussian processes approximation that also exploits the Laplacian eigenbasis. How does this method differ from the Hilbert space method in practice? If you have like some information on that.
Well, I do not feel qualified to answer this question because I have not heard or read about Hilbert space Gaussian process approximation. So I guess I'm not sure about the specific method that they're referring to.
Yeah, that's fine. That's fine. Yeah. Any other question from the audience? Seems like no other question.
No.
So maybe for last time we can ask if there is another question before we wrap up.
Is there anyone who has questions about his presentation?
We have 2 minutes, so if you have one quick question, maybe you can ask in 2 minutes. Okay.
Okay. Thank you, Alex, for this work. I'll probably see you at SIAM. So yeah, thank you so much for tuning in today.
All right, excellent. Thank you again for inviting me.
Excellent work. I really liked it. Thank you.
Thank you.
See you. Bye.
Bye.